So I start?
Yeah. So cool.
How to make it green?
Doesn't show?
It's okay?
No. Usually a red light is not.
I see. I think it works.
It works?
I think it works.
Okay.
Yesterday it has to be green. Like
So today not. Okay, so I explained that yesterday I talked about 4D n equals to 2 superconformal field theories. Or whatever they are, they have the Higgs branch invariants which are symplectic. Varieties which are in fact hyperkähler variety. And also we get a sure index which is some Q series. Which satisfies certain modular invariance property. And we get these invariants by considering map constructed by beam O from 4D theory to VOAs. And you get a Q series by considering a character of the VOAs, and also these Higgs branches by considering associated varieties. And so this 4D theory is very big, rich theory, and among them there are a large class of theories called Agras. So this is actually not. So this fact is actually a conjecture. So this is conjecture. I mean, I'm saying it's conjecture because it's not even clear at physical point of view. Even physical.
Conjecture.
Yeah, it's conjecture. And so for Agras-Douglas theories, corresponding VOAs a boundary admissible double algebras and Higgs branch identified with some intersection with some nilpotent closure and through this slice. But this is, as I said, this is a conjecture. It's really physical conjecture. So meaning that nothing is really defined mathematically. So I don't. So this is very interesting statement, and there are many interesting mathematical problem arising with this identification. But this statement itself, I don't know how to make a purely mathematical statement. However, there's another nice class of for the theories called classes theory. So maybe I write here. Where S stands for 6. So this theory comes from the 6-dimensional theory by dimensional reduction, as Sergei explained. So in Sergei's notation, so this theory is labeled by a flavor symmetry group G, which is a semi-simple group, and also a punctured Riemann surface. And this theory is obtained from 6-dimensional theory by doing the compactification on this Riemann surface. And the good news is that the 6th branch of this classes theory has been defined mathematically. Thanks to Moore and Tachikawa and Braverman and Finkelberg and Nakajima. So in this case, this conjecture can become a purely mathematical problem, and this is what I'm going to talk about today. Okay, so the Higgs branch are called Moore-Tachikawa varieties. So I'd like to talk about the Moore-Tachikawa varieties first. So Moore-Tachikawa reformulated this correspondence in terms of two-dimensional topological quantum field theories. So this is what I'm going to explain now. So because we are considering two-dimensional topology TQFT, so we consider the category of two Baudisms. So objects here are compact oriented one manifolds, which is just a disjoint union of S1s, the circles.
But at least corresponding four-dimensional theory, it defined at least physically.
Of course, it.
Physically, it means that what does it is Lagrangian or something.
It doesn't have Lagrangian in general, I don't think.
In this case, not.
No.
But it exists in some way. Yes.
It exists some way, yeah.
My dream to understand in what way, but
Anyway, so I cannot really answer your question. So, and morphism is compact oriented to manifolds whose boundary, so home B1 to B2 is this given one manifold. So it just look like this. So this is two circles, and this is one circle, and home is something like this. And so in this category, you can compose in obvious manner so you can just go here and get this. Two-bodism. And I remark that the identity morphism from S1 to S1 is the cylinder. And this category is a monoidal category. So you can define some tensor product, and the tensor product is just a decision union. So this is one category, and I also need a category of symplectic varieties. So this is category of so this, I say this is a category of symplectic varieties, but the objects here are not symplectic varieties, but a complex, a semi-simple group G, which correspond to flavor symmetry group of classes theory. And morphism here is given by symplectic varieties. So this is isomorphism class of symplectic variety X equipped with action of this group G1 and G2, and also action of C star, such that the action of Gi is Hamiltonian. So we have a moment map to the dual of real algebra GI. And also this cyst action dilates the symplectic form.
How do you compose them?
Yeah, I'm going to explain. So how we compose composition. So we have the two varieties from home. So want to compose the two varieties. And we have action of G1 and we have action of G2 and we have action of G2 and we have action of G3. So on the product we have a diagonal action of G2. So you can consider the corresponding symplectic reduction. This is
Well, okay, so what's the symplectic variety?
I don't want to be so much precise.
I mean, it makes sense for some Poisson steps or something like that, but it doesn't make sense for symplectic varieties.
What do you mean?
Well, I mean, the action doesn't need to be free, and
It doesn't actually need to be free. So in this case, I replace by derived reduction or corresponding BRST reduction.
so we are dealing with derived Poisson steps.
But at the end, it's enough going to have nice. At least for G not 0, this is going to be action free.
Okay.
So you don't have to worry about it. Yeah, so this is so this is a level set and quotient out by the diagonal action of G's. So it's natural to ask what is identity morphism from G to G. And this is a cotangent bundle to G.
Star G.
T star of G, yeah. Which is just a G cross G star. Why this is so? So you want to show this product give you y back. And so moment map here is just a projection to the so this is the level set. So this is what so this is because this is just a projection. The level set is where so this is a moment map for y. But this is isomorphic to G cross y, and we get y back. So this is monoidal category. again. And tensor product is just a Cartesian product of symplectic varieties. The theorem which was proved by Braverman and Finkelberg Nakajima and conjectured by Moore and Tachikawa states the following. So you choose your favorite G, then there exists a monoidal functor from the category of two-Bodism to the category of symplectic varieties, which satisfy the following conditions. So first, you have to decide where objects go. So S1 goes to this given group G. And identity morphism have to go to identity morphism. The cylinder have to go to a cotangent bundle to G. The real condition is that the image of cap has to go to equivariant constant slowly slice. So S is a slowly slice for principal nilpotent element. So E, H, F are regular. And so this is symplectic variety because by constant you can, this is isomorphic to this space, and this is, if there's no if this is just a cotangent bundle to G over G over N. So this is a twisted cotangent bundle over G over N.
Just a reduction of this star G by
Exactly. Yeah. You see.
I think the easiest way to see the symplectic form is just that the right embeds to T star of G, and it's a symplectic subvariety.
Sorry?
So the variety G times S embeds into T star G, and it's a symplectic subvariety.
Oh. But you can also say it like this also.
So do you only need to specify the value on the half cell, on one half cell, on one pole, to read the other pole as well?
Other cone as well. Other cone as well. They both go to this.
But one is sort of opposite of the other.
Yeah. So now, so what this statement mean? So, if you believe this theorem, you get a zoo of symplectic varieties coming from two Bodhisms. And these symplectic varieties are exactly Higgs branches of class S theories. So the Higgs branch of SG.
May I ask a question?
Yes?
Maybe it's a small question to Misha. So somehow, let me ask it in a straightforward way. Why is it a theorem? So what is the statement of this chart? So, what does it mean to check existence? Is it kind of to check the relations, or to check the?
You have to check. You have to check the. You have to check, for example, associativity. So. Yeah. So Higgs branch of this class S associated with this Riemann surface is supposed to be the image of two Bodhism with the same genus. For connected ones. And the n is a number of boundaries. So let me explain. So this is a very non-trivial statement. So, and I want to explain this by showing you some examples. For SL2, so this is already Sergei explained. The image of a pant, which is the same as Higgs branch of what? Three-pointed Riemann P1 is the C2 C2 tensor C2 tensor C2. So there's a natural action of SL2 on C2, which so this is naturally symplectic variety, and this induces symplectic structure here equipped with three commuting action SL2 corresponding to these boundaries. So this is not surprising.
Should we put superscript BFN?
Yeah. If you look at next example, Yeah, let's look at next example. So how about the image of Buddhism with 4 boundaries? This is not the 4 tensor product of C2, but what you get here is a minimal nilpotent oblique closure in D4. So why D4? So if you write Dinkin diagram, you find 3 commuting action of Bessel 2 here. But if you write affine Dinkin diagram, you find extra action. So you have 4 commuting action Bessel 2 corresponding to 4 boundaries. So as you can see from this example, more Tachikawa varieties can be singular, so you have to allow a singularity to consider more Tachikawa varieties. So mostly these varieties are singulars.
But as you explained, minimal orbit here as Higgs branch in some other sphere. It's not a,
Yeah, there's some intersection. This is the intersection.
some coincidence.
The same theory has several descriptions. And so you have to check, for example, so the theorem gives you many non-trivial identity. For example, because this map is a functor, you should have this identity. And this is, as I said, a minimal nilpotent oblique closure in D4. But this is just C2 tensor 3 times C2 tensor 3. So this is symplectic reduction of this affine space. So this is already non-trivial statement to me, but this is well known for physicists and called ADHM construction of minimal nilpotent oblique closure. So now let us look at SL3. And then the image of pants is maybe already expect, but minimal nilpotent oblique closure in E6. So in E6 you find in extended Deakin diagram 3 commuting action of SL2 corresponding to 3 boundaries. But you cannot continue like this because you go out of Deakin diagram if you ranking this. So these varieties, I think, are completely new symplectic varieties, which satisfies a bunch of interesting relation like this. I should So any two Bodhism can be obtained from cap. Maybe you don't need cylinder, but it's right. And also pants. So what you actually have to do is by compositions, by compositions. So it's enough. So it's enough to define the image of pants. And to check the compatibility condition. So you basically have to check this associativity like this. For SL2, this associativity follows from to reality of this minimal nilpotent oblique closure. But in general, it's a quite non-trivial problem. And even this, we don't have a explicit, straightforward description for higher alpha alpha G.
So this is the only condition which we have.
Yeah, basically, yeah.
What is the description of this variety?
I'm going to how they construct.
Yeah, how?
Yeah, I'm going to explain it. Yeah, and the proof is very non-trivial. So as I said, it's enough to construct image of pants. So in particular, it's enough to construct image of a genus zero Bodhism. So So how did I write? So B0R. So this is Bodhism with R boundaries. To define this, you consider a fine Grassmannian for the dual group. Then you have a geometric Satake. Which said, so the category of equivariant pervasives can be identified the category of finite dimensional representation of G. And here you have a regular representation of G. And the corresponding sheaf is called a regular sheaf. And you consider a box tensor product of this regular sheaf on the product of a fine Grassmannian, and you consider a Schlick pullback of this sheaf. And they showed this is a commutative ring object, and so that if you consider a corresponding equivariant homology, you get a commutative algebra. So you can take a spectrum. And this is the definition, the construction of the symplectic varieties. So let's say this is X. Sorry? This is a diagonal embedding. From GR to a product of GR.
So for R equals 3 and J equals S2, we will get this answer, yes?
Yeah, so this is very non-trivial state. Yeah, so I repeat because it's quite non-trivial. So this XR is symplectic and equipped with Hamiltonian action of GR. It's R copy of GR. So this is already non-trivial statement. And X1 is G cross. So this is equivariant through this slice. And X2 is cotangent band to G. And associativity horn, so which is delta G. Yeah, so you yeah, so this is XS. So for example, you have you compose this Buddhism and you lose two boundaries. And so this simplicity variety is conic for equals to less equal 3 or greater or equal to 3. Well, so this is actually only physical case.
So, may I ask again? So when you say symplectic variety, what precisely does this mean?
It's a Poisson variety, irreducible Poisson variety.
For example, there is a statement this algebra here is reduced.
Reducibility is always reduced. At least type A it's reduced. It should be reduced, but the proof is, as far as in the paper, it's written only for type A. But if it's not is it?
For genus 0.
Genus 0, yeah.
So it's just Poisson algebraic variety.
Yeah. And yeah, symplectic in its smooth locus. And the dimension of so this is easy to guess from this picture around. So maybe I should remark for type A. So I said I explained that the Higgs branch for this theory is closely related to the Coulomb branch of 3D gauge theories. And for type A, this is indeed the case. So this XR is Coulomb branch of 3D quiver gauge theory associated with so this kind of quiver. So there's R legs. Okay, so class S theory.
So it's like you take a whole bunch of cotangent bundles to flaperite and then you just reduce by the diagonal action of GLM, right?
Okay, so for class S theory, so this 6-branch map became a really mathematical statement. So this we can replace by monoidal functor from B2 to the symplectic varieties. And the image of two Buddhism are the Higgs branches. So now, I want to rate these two vertex algebras. So what I'm going to do now is to upgrade this functor to the setting of vertex algebra. So I'm going to define a category of vertex algebra. and construct similar functor and show that this diagram commutes.
Not factor is just associated, right?
Well, yeah. And the existence of such a functor was already conjectured by B and all, because so this picture really comes from a six-dimensional theory, and the same picture gives you this kind of functor, at least conjecture existence of such a functor. Okay, so I'm going to define the category of vertex algebras. So I don't change objects from category of symplectic varieties. So objects are the same. So it's complex, the same simple groups, but the morphism are given by vertex algebras. So from G1 to G2 are isomorphism class of vertex operator algebra objects in this tensor product. So then I'll explain what is vertex algebra object, but let me explain. So GI is a Lie algebra of GI, and so if it has several simple components, I consider corresponding direct sum of Katsumudi affine algebra, and then you can define Kazan-Lustig category. So this is a full subcategory of O on which G acts semi-simply. And I consider the action representation at critical level. So all component acts as at critical level. And here also. So vertex operator object means, so this is a vertex operator algebra. So equipped with a vertex algebra homomorphism of this tensor product of two affine vertex algebras, which induces action of G1 hat and G2 hat here. And as a G1 hat and G2 hat module, this belongs to this category. Yeah, so in particular, so V is equipped as an action of G1 hat at critical, and G2 hat at critical. So how I compose two vertex algebras. So before it was a symplectic reduction. And symplectic reduction has a affine analog, which is BRST reduction. So I use BRST reduction. So you have V1 and V2. So I compose by taking, we have action of G2 hat in common. So we can take a diagonal action of G2 here. So this acts diagonally. And the level is minus 2 times H2 check. And at this level you can, this BRST cohomology is defined. For other levels you cannot define. So this is why we have to choose a critical level. So that's 2 times is this level. And because I didn't touch the action of G1 hat and G3 hat, and G2 hat and action of G1 hat and G3 hat remains in this cohomology. And because this is defined as BRST, it has natural vertex operator algebra structure.
So how is the statement of some cohomology vanished?
For genus 0, yes.
So like you only have one vanishing cohomology?
Yeah. So in nice situation, we are vanishing holes. Associated variety of this product is in fact the product of symplectic variety as I defined. So this is a symplectic reduction with respect to the diagonal action of G2. And this one is monoidal category. Again. And so tensor product of vertex algebra is usual tensor product. Yeah, maybe I stop here and continue.